the prevailing theory that Westerners eat sweets and Asians don't. So this has been strongly confirmed. So the grand prize goes to Matthew Fletcher. So I'd like to award the prize of one real brownie for finding this very nice 2x6 matrix. So a grand prize. And of course, I kept one for myself, or anybody else has a solution. Okay, so that was the grand prize. So then we have this 2x6 matrix. We look at the row space. That's a line in P5 over the, for instance, over this field. And the corresponding tropical Plücker vector is exactly the one we had yesterday at the end. And then the corresponding tree is a caterpillar tree. We learned yesterday there are 105 labeled trees, 90 snowflakes, and 15 caterpillars. So this is one of the 15 caterpillars.
If I take the columns, the first column and the fourth column, what is the determinant?
This one and this one, the determinant is,
I must have 0.
I have 1 plus a higher order term. So the determinant is 2 minus t minus this. So the determinant is 1 minus 2 times t, which has value 0. Right, so by this I simply mean the vector that has coordinates 1 here and it has coordinates 0 everywhere else. This is a 0, 1 vector. This is a 0, 1 vector with 12 zeros and 3 ones. Does that answer your question? Yeah? Okay. Okay, so welcome back for lecture 7. So I'd like to tell you about morphisms in tropical geometry, and then look at the morphisms that define so-called secant varieties. So we're going to do this very concretely. Let's suppose we have a morphism in ordinary algebraic geometry, by which I'll, for simplicity, simply mean a polynomial map. Okay? Let's just say we have a polynomial map between affine spaces from D space to N space. This could be a rational map too, but let's just start with the polynomial map for simplicity. Then we can tropicalize the map So the tropicalization of a map from D space to N space, polynomial map, which I'll denote by capital F, is a map from Rd to Rn, which is piecewise linear. Which is the piecewise linear map that's defined the obvious way, okay? Namely, the coordinates, the ith coordinate of Fi is simply the tropicalization of little fi. So we simply replace each, we have n polynomials and d variables. We take each of these n polynomials and replace each of them by the corresponding tropical polynomial. Now, of course, if the valuation is trivial, so if all the coefficients of these polynomials have value 0, then we know that Fi is the support function of the Newton polytope. Okay? So this is even interesting, very interesting over a field with trivial valuation. So there we have n Newton polytopes in d-dimensional space, and we make a map, a piecewise linear map from d space to n space by minimizing, we evaluate this map by solving n linear programs, right? We're minimizing n linear functions over these various d-dimensional polytopes. Now, the central question here, is it true that the image of the tropicalization is equal to the tropicalization of the image? Okay. So is it true? So here we take in ordinary algebraic geometry, we take the image, so we have to, this may not be closed, so we have to pass to the Zariski closure. Okay, so then we tropicalize this variety. Is that equal to the image of the tropicalization? So does tropicalization commute with morphisms? That's the question. Okay. Well, the answer is no, right? That makes it interesting. So the answer is the following. We always have that the left-hand side is contained in the right-hand side. So the image of the tropicalization is always contained in the tropicalization of the image of a morphism. But equality is usually false. It's usually far from true. So equality rarely holds. There are some special circumstances where it does hold, but usually this is a strict inequality. So that's the fundamental problem, is that the image of the tropicalization is not equal. It's strictly contained in the tropicalization of the image. Let me give you a very, very elementary one-dimensional example. So here's an example. Let's do this over the complex numbers with trivial valuation. So let's do this with the trivial valuation. And d is 1 and n is 2. So we're given two polynomials in one variable. I'm going to call them p of t and q of t. So this is a plane curve. So the image is a parametric, parametrized plane curve, where p and q are some polynomials, and I'm going to take specific polynomials. I'm going to take p of t to be a degree 4 polynomial, t squared times t to the minus 1 times t to the minus 2 squared. And then q of t, I'm going to take t times t minus 2 squared, this cubic polynomial. And I'm writing them in factored form. This factored form is a hint for exercise number 1 that was just handed out. Today is our last chance in the afternoon to discuss exercises, so please take a look. There will be no such session tomorrow. And this factored form of the parametrization is a hint for exercise 1. Anyway, so let's look at this parametrized curve in the plane. Well, how do you calculate the image? So let's calculate the image. Let's calculate the equation of this curve in the plane. But the way we like to think about it let's look at the graph. I'm going to do this very, very slowly. So the graph of this map is a variety in three-dimensional space. So this is going to be a very slow example. So we're going to look at the graph of this map. I have the line. I map it into the plane. And it's the variety of this ideal, x minus p of t, y minus q of t. Okay? So this complete intersection surface is the graph of this map. Okay? Now, whenever you have a map from d space to n space, well, to calculate the image, you take the graph and you project it onto the second factor. So calculating the image of a map means projecting the graph onto the second factor. So let's do that, right? So the image, so this I defines now a space curve, and the image of the map F is the plane curve. With equation R, X, and Y. Well, how do you calculate this? Of course, you just eliminate, right? So you just take I and you pass to the elimination ideal, and then the principal generator, the generator of this principal ideal, is the resultant. So it's the resultant with respect to t of these two polynomials, x minus p of t, y minus q of t. So that's all trivial stuff which you learned long time ago in your undergraduate days when you studied Coxeter-O'Shea. You all learned about resultants. So you eliminate t from these two equations, and you get a polynomial in two variables, which is y to the fourth minus x cubed plus 7 x squared y minus 9 xy squared minus y cubed plus 8 xy. That's what you get. You get this irreducible polynomial. Okay? Now, just for the record, let me also note the Newton polytope. I'm going to draw the Newton polytope of this polynomial for you. So here we have, let me draw this in yellow, y to the fourth, y cubed. Then here we have x, y squared. We have xy. We have x squared y. And then down here we have, what, x cubed. Okay, so the Newton polytope is going to be a quadrangle that looks like this. This is the Newton polytope of the implicit equation. Okay, so we have a parametric curve in the plane, and this is the implicit equation. So now let's see what happens if we try to do this tropically. Well, there are two things that go wrong. So first of all, let's look at the tropicalization of the graph. Let's tropicalize the graph. So the tropicalization of I consists of the 5 rays, consists of 5 rays in three-dimensional space, spanned by the following vectors. You take 1, 0, 0, 2, 1, 0. So the way this is done here, t is the, let me see, t is the first coordinate. So the coordinates are t, x, and y. So that's 1, 0, 0, 2, 1, 0, 1, 2, 0, minus 4, minus 3, minus 1, and then 0, 0, 1. Okay? That's the trough. You type this into GFAN. These are the rays that come back, and these are balanced, right? Those 5 vectors sum to 0. They have to be balanced, okay, by the residue theorem, by complex analysis, right? So from complex analysis. You know the residue theorem, right? So on the Riemann sphere, for instance, the sum of the residues is 0, right? That's the balancing condition. So, okay. Now, these two guys, this is a very nice complete intersection, but notice they do not form a tropical basis. Let me just remark that these two equations, the naive graph is actually too large. So this is strictly contained in the pre-variety. In the pre-variety that you just get by tropicalizing this and this, right? Because if you tropicalize the two equations separately without running GFAN, you just look at these two equations separately. So this is the tropical hypersurface. Let me use capital coordinates. X plus t to the fourth plus 0 is the first tropical polynomial, and y plus t cubed plus 0 is the tropicalization of the second polynomial. That's too large. So this is going to be strictly larger than the 5 rays. So this contains an entire orthant. It contains all points x comma y in 3 space where x and y are non-negative. Okay? So the graph is, you really have to calculate the graph carefully, the tropical graph, but not naively. On the other hand, yes. Oh, yes, absolutely. I'm sorry. Absolutely. Yeah, I mean P and Q. Thank you. Okay. Now it's okay. Thank you. Okay? So the pre-variety that you get is too large. But now you have the tropical variety, but we can take the tropical variety, project it. That projects correctly. On the other hand, if you take the image of the tropical morphism, right? So what's the tropical morphism here? It's the map from R to R squared that takes T to the tropicalization of P, which is T to the fourth plus 0, and the tropicalization of Q, which is T cubed plus 0. This is strictly contained. So this is an example where we have strict containment. Contained in the tropical curve given by the resultant. Now, what's the tropical curve given by the resultant? Well, these are the 4 rays gotten by projecting tau of I. Okay, so I simply, t is the first coordinate. So that will give me the correct tropical curve. I simply take those 5 rays and I project on the last onto the last two coordinates. And I think, so then if I project onto the last, maybe I didn't do this quite right. Oh yeah, no, I project onto the last two coordinates, then this ray goes away. It becomes the origin. So all that survives is, what survives is this ray, this ray, this ray, and this ray. And of course, what we get is the inner normal fan of the red Newton polytope. So that's 2, 0, 0, 1. And then, is that true? Minus, I think I made a mistake somewhere. 1, 0. Should be the inner normals. This one. Oh yeah, 1, 0 is this one. Okay, let's try again. So this is 1, 0. And do they sum to 0? They do, huh? Maybe I labeled the coordinates incorrectly. That's a possibility. And we have -4, -3. That's like this. Maybe I want the first two coordinates. Does this make sense? Oh, yeah, I'm sorry. Okay, let's try again. Sorry, guys. Okay. So t is the last coordinate. I labeled incorrectly. So it goes x, y, and t. So I'm projecting onto the first two coordinates. X, y here, x, y here, x, y here, x, y here. This point goes away. It becomes the origin. This becomes -4, -3. That's the inner normal to this edge. This one becomes 1, 2 up here. That's the inner normal to that edge. And then there's one more, 2, 1. Okay, that's that one. And that's the tropical curve. Okay? Now, what is the image of tropicalization? Well, the image of the tropicalization, now look at this map, right? So this map takes a real number and it maps it to the maximum of 0 and 4t and the maximum of 0 and 3t, minimum. So if t is positive, right, it's going to land just here. So for every positive real number t, we're going to land here. For every negative number t, we're going to land here. Okay? So in this example, we have the image of the tropicalization. It's just this blue half ray. That's all. That's the image of the tropicalization of the morphism. But the true tropicalization of the image is this one. Okay? So this is like in the American story, right? There's a mama bear. Do you know about this? Mama bear, papa bear, and kid bear, right? So there's one pre-variety that's too large. If you take the naive graph and project it down, you get something that's too large. That's papa bear. If you take the image of the tropical morphism, it's way too small. You get just the blue half ray. But if you take the tropicalization of the image, it's just right. That's exactly the inner normal fan of the Newton polytope. Now, this is a good example. Now, this example also illustrates something that for which I don't have time. So in computer algebra, people are very, very interested in having fast algorithm for elimination and implicitization. And there are existing methods, Grobner bases, resultants, and so on, and they often don't work in practice. So if you have a larger, medium to large size example, existing elimination and implicitization methods don't work. But there's a new body of literature on tropical elimination and tropical implicitization that can do quite a few problems that couldn't be done so far. So I don't have time to talk about this. But the basic idea of tropical implicitization is the following. We're going to compute this polynomial using tropical methods without Grobner bases. We're going to do this intersection, this elimination ideal, as follows. We start from the equations. We look at the graph. We calculate the true graph, T of I, by combinatorial methods. But we have to do it careful. That's the papa bear situation. So we carefully, by combinatorial methods, calculate this. Then we project it down by dropping the last coordinate. Then we get that red fan. Then from that red fan, we're going to recover that red Newton polytope. From that red Newton polytope, we're going to make an ansatz with indeterminate coefficients for each of the yellow monomials. Then we're going to ask our friends in numerical linear algebra to solve the linear system of equations. And there we go, we get the coefficients. Okay? So tropical elimination, tropical implicitization takes parametrized varieties, takes the parametrization, but instead of doing some kind of Grobner elimination, we're going to go like this. Okay? So that's something I will not speak about. Instead, I like to speak about secant varieties. Let's do a quick in-class exercise. So I appreciate those who are still coming. So let's make sure everybody is awake. Let's do a little in-class exercise. How do I get this vertex? Oh, well, if I have this fan, if I know this fan, then there's a unique polytope. There's a unique polytope up to translation that has this normal fan with these edge lengths up to translation. But I want to make an irreducible polynomial, so it's unique by translation. So I have to kind of have a pure power factor term of a and y. So then you get the red polytope. Then you take the red polytope and then you ask the software for enumerating all lattice points in the polytope. So then you take Latte, such a software system. Then you take the red polytope and you say, give me all yellow lattice points in the red polytope, and it comes back in no time. Okay? So you just enumerate the yellow lattice points in the, and then from that you recover the polynomial. So there are situations, so nowadays, there are situations you no longer use Grobner basis or resultants to eliminate, but you go by tropical methods. Okay, let's do an exercise, in-class exercise.
So there are examples that were previously unglobal?
Absolutely, yes, absolutely. Yeah, there's a very nice paper. Right, there's a conference right now, MEGA, Méthode effective en géométrie algébraïque. And there's one or two papers, I think 2 papers on this. Yeah, they can do examples that you cannot do otherwise. And I might say a little bit more about this when I talk about discriminants tomorrow at the 10th lecture. Okay, let's consider, but I want to make sure everybody understands the difference between blue and red. So let's consider a linear map. Consider a linear, suppose F is a linear map from K2 to K4. Okay, so which we can, since we like lines, regard it as parametrization of a line. L, which is the image of F inside, let's say, P3. And so K is some field with a non-trivial valuation. And the exercise is to draw the image of F, the image of the tropicalization inside the tropicalization of the image. So can you draw, in this example, the image of the tropical map inside the tropical line? It's a do now exercise. So you're encouraged to do this now. Just draw an example how this might look like. Okay, let's do red. So how does tau of L look like? What's the tropicalization of the image look like? So the image is regarded as a line in 3-dimensional space. So Anybody like to draw a line in 3 space? Would you like to draw a line in 3 space? So tau of L is a line. T of L is a line in 3 space. Could you draw a line? Anybody can draw a line in 3 space? Would you like to draw a line?